Welcome to this concept explainer. It's brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are taking a deep dive into the microscopic world of current electricity from Unit 3. We'll be focusing specifically on the drift of electrons and the origin of resistivity. We promise a simple, exam-safe explanation that you'll understand clearly and, more importantly, remember for your exams. Okay, let's start with a question, a simple one. You switch on a light and the bulb lights up instantly, right?
Yes, of course, the moment you flip the switch.
It feels instantaneous. But what if I told you that the electrons inside that wire, the actual particles carrying the charge, are moving slower than a snail?
Slower than a snail. Wait. How can that be possible? If the electrons themselves are so slow, why is the effect immediate? That doesn't make any sense.
It is a bit of a paradox, isn't it? And that's exactly what we're going to unpack today.
Yep.
If we could actually track a single electron in a typical copper wire, say, in your house, it would be shuffling along at about 1 millimeter per second.
1 millimeter per second.
Actually, it's even less, around 0.074 millimeters per second. Yet, the bulb lights up instantly. This disconnect, this huge gap between the fast signal and the slow carriers, is the whole key to understanding current at a microscopic level. So what's really going on inside that wire? Well, the electrons are actually living a kind of dual life. They have two different motions happening at the same time. First, there's what we call thermal motion.
Okay.
Because the wire is at room temperature, the free electrons have thermal energy. This makes them jiggle and zip around randomly in every possible direction. And their speed here is enormous. We're talking up to 10 to the power of 6 meters per second.
1 million meters per second. That's incredibly fast. But if they're moving so fast already, why is there no current in a wire just lying on the table?
That is the perfect question. It gets right to the heart of it. The motion is fast, yes, but it is completely random. It's chaotic. For every electron moving up, there's another one moving down. Left, right, forwards, backwards.
So they all cancel each other out.
Exactly. The average velocity of all the electrons together is 0. No net movement means no current. Now, everything changes the moment we connect a battery.
The electric field.
Yes. An electric field, E, is established across the wire. This field puts a tiny, tiny force on every single free electron. And this force adds a small, coordinated bias, a little push to all that random high-speed jiggling.
So the push on top of the random motion.
Precisely. And this tiny, slow, coordinated movement is what we call drift motion. That's the current. Let's use an analogy to make this really clear. Think of a very crowded dance floor. The people are the electrons. They are all dancing wildly, jumping around, moving in random directions. That's the thermal motion.
Okay, I can picture that. A lot of chaos.
A lot of chaos. Now imagine the DJ suddenly tilts the entire dance floor just a little bit, a very gentle slope.
So people would still be dancing wildly,
But they would all slowly, as a group, start to drift downhill. Their random dancing is still the main thing they're doing, but the whole crowd now has a slow, unified movement in one direction because of that slope.
And that slope is the electric field.
You've got it. That gentle slope is the electric field, and that slow, collective movement downhill, that is the drift velocity, the current. Now, to bring this back to the wire, just picture the atomic lattice. You have these fixed positive ions, the atoms of the copper, all lined up, and the free electrons are like a blue fog whizzing between them.
And constantly bumping into them, my opinion.
Constantly. They are always colliding with these lattice ions. And these collisions are actually what oppose the drift. This opposition, this constant bumping and losing of momentum, that is the microscopic origin of resistivity.
So the collisions are what make it resistance. They slow down that organized drift.
Perfectly put. Without collisions, the electrons would just keep accelerating forever under the electric field, which can't happen. The collisions create a sort of traffic jam that keeps the average drift velocity very, very small. Okay, so now that we have the physical picture, let's look at how NSERT defines this technically. The wording here is really important for your exams. The relationship between the current, I, and this drift velocity is given by a key formula. Could you read that for us?
Yes. The microscopic form of current is I equals N times E times A times V subscript D, where N is the number density of free electrons, E is the charge of an electron, A is the cross-sectional area, and VD is the drift velocity.
Excellent. That formula, I equals NEAVD, connects the big picture current, I, to all tiny microscopic details. Now, what about VD itself? We said it comes from the electric field.
And what about that term tau? I've seen that in the textbook.
Yes, tau, the relaxation time. Let's build this up step by step, just like you would in an exam derivation. Step 1 is acceleration. Between two collisions, the electric field, E, makes the electron accelerate. The force is E times E, so the acceleration A is just EE divided by m, the mass of the electron.
Okay, simple F equals ma.
Exactly. Step 2 is the collision. The electron accelerates, gains a bit of forward velocity, and then bang, it collides with a lattice ion and loses that forward momentum. Its velocity is essentially reset.
So how does it ever get a steady speed?
Through averaging. This is where tau, the relaxation time, comes in. Tau is the average time an electron travels between two collisions. So step 3, we define drift velocity. Since the electron accelerates for an average time tau, the average velocity it gains is just its acceleration times that time. So Vd equals a times tau.
Which means Vd is EE by m times tau.
Perfect. Vd equals EEm multiplied by tau. You can see right there that drift velocity is directly proportional to the electric field E. Double the field, you double the drift velocity. And now for the final step, step 4. The origin of resistivity. This is the beautiful part. We just substitute our new expression for Vd back into the current equation. I equals NEAVD.
Okay, so you put the Vd formula into the I formula.
Yes, and when you rearrange the terms to look like Ohm's law, you find the microscopic formula for resistivity, rho. It turns out that rho equals m divided by Ne squared tau.
M divided by Ne squared tau.
M divided by Ne squared tau. So if tau is small, that means collisions are happening very often.
Yes.
And if tau is in the denominator, a small tau means a big resistivity. You've nailed the concept. A small relaxation time means frequent collisions. Frequent collisions mean more opposition to drift. And more opposition means higher resistivity. That's the entire story of resistance at the microscopic level. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROSSAM.com. And this relationship, by the way, is the microscopic proof of Ohm's law. Since current is proportional to drift velocity, and drift velocity is proportional to the electric field, it means current is proportional to the field. That's Ohm's law in its most fundamental form. Now let's quickly check the numbers we talked about earlier. If you take copper, plug in the known values for Ne and a standard 1 ampere current, and you solve for Vd, you really do get a number around 10 to the power minus 4 meters per second. It confirms that incredibly slow speed.
So coming back to the light bulb puzzle, it turns on instantly because the electric field signal travels at nearly the speed of light.
Exactly. The field is the command. And that command tells all the electrons everywhere in the wire to start drifting at the exact same moment. It's not one electron making the whole journey. It's a simultaneous shuffle of all the electrons already there. Okay, let's move on to the silent killers. These are the common misconceptions that can really cost you marks. Misconception number 1 is probably the most common. Students write, current is the speed of electrons.
Oh, I can see why people would think that. It's very intuitive.
It is, but it's completely wrong. Current, I, is the rate of charge flow. It's about how much charge passes a point per second. Drift velocity, VAD, is the actual speed, which we know is slow.
Right, so current is how much, not how fast.
Remember that hook. Current measures how much charge passes per second, not how fast it moves. Okay, misconception number 2 goes back to our hook. If electrons drift slowly, the light must turn on slowly.
And the correct idea is that the signal is fast, but the carriers are slow.
Perfect. The electric field propagates almost instantly, causing all electrons to drift simultaneously. Think of a long pipe filled with marbles. You push one in at one end and one pops out the other end instantly, even though each individual marble only moved a tiny bit.
That's a good analogy.
Remember, the signal travels fast, the charge carriers travel slowly. Finally, misconception 3 is about what causes resistance. Students will write something like, resistance is because electrons are lazy or get stuck.
Which is wrong. It's not about being lazy.
Not at all. It's a violent process. Resistance arises from collisions. It's about momentum being transferred from the electrons to the fixed ions in the lattice. You must use the word collision in your answer.
So to be clear, the corrected version is, resistance is caused by collisions between the drifting electrons and the lattice ions. More frequent collisions mean a shorter relaxation time, tau, and therefore higher resistivity.
That is a full marks answer. Exactly. Resistance equals collisions limiting drift. Now, to lock this all in, let's use a few memory anchors. For the drift velocity formula, Vd equals Em tau. Just think of this story. The electric field, E, is the push. The electron E feels that push. Its mass, m, resists the acceleration. And tau is the small amount of time it gets to accelerate before the next collision.
E pushes E, m resists, tau is the time.
Okay. And for the overall concept, just remember this phrase. Electrons drift slowly but collide constantly. It's the drift coordination that creates current. And finally, a little physical gesture you can do. Hold your hand out, palm down. Now, wiggle your fingers really fast and randomly. That's the thermal motion.
Okay, got it.
Now, while you keep wiggling your fingers, slowly tilt your entire hand forward. That slow tilt, that is the drift motion superimposed on the random wiggling. It's a great way to visualize both motions at once. So let's summarize this entire deep dive into 3 final exam safe points. 1. Electric current, I, is the result of a coordinated drift of free electrons. The formula is I equals NEAVD, and that drift velocity is extremely small, typically around 10 to the power minus 4 meters per second. 2. Resistivity. Rho is the material's opposition to this drift, and it's caused by collisions. Microscopically, its formula is rho equals m divided by ne squared tau. And 3, a good conductor like copper has low resistivity because it has a very large number of free electrons, n, and a relatively long relaxation time, tau, which means fewer collisions. To get maximum marks not just in physics, but also in 12th CBSE chemistry and maths, visit ProfSam.com.
As ProfSam, right?
Yes, ProfSam.com. Thank you for diving deep with us. We hope this gives you absolute clarity on the topic. See you in the next Concept Explainer.